We are going to be looking at 5F. We should be able to get through most of it today. We may need to finish up a little bit on Tuesday of next week. But again, I think we can get through most of it today. It's just a really big section because we look at a lot of applications of these exponential formulas, and then we need to use logarithms to often solve for those values. So that's what we're going to be doing today. I hope that what you will get from today is that logarithms are really useful, that we need them, even though they might feel awkward. And then I hope you start to see that we will go through the same steps every single time to solve these. So those are my goals for today. So we'll just jump right into it, okay? So I'm going to share my whole screen over here because I want us to be able to have our calculator at the same time. Because again, it's really important that we know how to evaluate these based upon what we're putting into our calculator, because if you don't know the steps, that makes it that much harder. So you'll notice the first one, again, we're in 5F. We did application 1 on Tuesday when we talked about pH scale. And now we're looking at the idea of continuous exponential growth or decay. We kind of talked about continuous growth yesterday when I was going through the quiz. And so what we're given is initial population of mice is found to be 10. After 100 days, the population was 40. What is the growth rate of the mice? Write the continuous exponential growth function to model the situation. So I'm giving you the function at the top, or the generic formula for it. So it says Q of t, and Q of t, all of that means is a quantity at a specific time. So we've got Q of t equals Q sub 0. So Q sub 0 is the initial quantity times e to the RT. So R is our rate. If it's positive, then we're experiencing exponential growth. If your rate is negative, then you're getting exponential decay. So R is our rate, and then T is your time. Okay. So what information do they give us? It says the initial population is found to be 10. So at T equals 0, our quantity is 10. After 100 days, the population was 40. So now we have at T equals 100, our quantity is 40. So we're going to need to use those two pieces of information. And it says, what is the growth rate of the mice? Write a continuous exponential growth function to model the situation. So this statement here where it says continuous exponential growth, when we see the words continuous exponential, that means that we have to use this formula. Okay, I want that to trigger in your head, like, oh, I see the word continuous, I've got to go with that. So what that tells us is that we've got our quantity after time t equals our initial quantity at time 0 times e to the RT. So let's plug in what we know. What we know is that at time 0, we have 10, okay? So that means this is my Q sub 0 amount. So I can say after a certain amount of time, I've got 10 times e to the RT. So we still have 3 variables basically here, and we're trying to solve for R. So we need to use the other set of information that they provided us, which is that after 100 days, our quantity was 40. So now that we have sort of an initial amount, we can go and use these pieces. So this Q is 40. That's really our Q of t amount after 100 days. So we'll plug 40 in for Q of t. That's equal to 10 times e to the R times 100. So now we've created an equation where we only have one variable. Yes, I know E looks like a variable, but remember E represents a number, right? R is the variable, our rate here, that we don't know that we need to solve for. So when we were looking at our problems in 5E, there we go. We had problems like this, right? We had a variable in the exponent that we had to solve for. And so we needed to go through the steps to isolate that. If you remember, we wanted to think about this as being two blocks. I've got 10 times this stuff. Now, I want to get to that variable, and in order to get to that variable, I need to get the 10 off, meaning I need to get rid of it, and in order to get rid of it, I need to divide. So I'm going to divide both sides by 10. So 40 divided by 10 is equal to 4. So now I have 4 equals e to the 100r. Now, we're trying to get to that exponent, right? And in order to get to that exponent, we need to switch it from logarithmic format to log format, right? Or excuse me, from exponential to logarithmic. Since we have e, we can say the natural log of 4 is equal to 100r, because ln base e of 4 equals 100, right? That's my method that I can go through here. Now that I have this isolated, I now don't have that exponent there anymore, right? It's just written as 100r. So it will, when you're solving these, you may look at that and go, oh, well, I just need to take the natural log of 4. But remember, the natural log of 4 is most likely a non-terminating number. So if I do ln of 4, you can see that's a decimal that goes on a really long time. So we don't want to evaluate that early and have, and have us try to round it and be off. So instead, we're going to leave that as ln of 4, and we're going to continue to try to isolate r. To isolate r, we're going to divide both sides by 100. And so we're left with r is equal to the natural log of 4 over 100. And now that's the whole piece that we want to put into our calculator. So if we go back to Desmos, we can put parentheses around the ln of 4 so that we can do the division key, and that will make us have a division problem. And this gives us a value, right? So this tells us that r is equal to 0.013. And I like to take these out 4 decimal places, so you can see that it's 0.01386, blah, blah, blah. So I'm going to round that to 0.0139. So we have found the growth rate. That was his first question. What was the growth rate? We found that. And now we need to go back and write the initial model. So we have part of it right here. Okay, so if you remember, we had already started with this piece right here. But we had q of t equals 10 times e to the rt. And we can't have 2 variables in that exponent if we're going to evaluate the formula later. We need to only have 1 value. And so now what we can do is we can plug that 0.0139 in for r. So our final model is going to be q of t equals 10 times e to the 0.0139t. I know that's really squished up there. But that is our final model right here. And so that's what we're going to use for the next part of this problem. Part B says, when did the population of mice double? So when they're asking about the population doubling, they're saying, when was it twice the original amount? And another way to say when was it, meaning it means how long did it take for it to double. So if we're looking at twice the original amount, what was our original quantity of mice? Well, the initial population was 10. So if we take our initial population of 10 and we multiply it by 2, we have a quantity of 20. So that's going to be our new quantity amount, okay? So remember, the quantity of mice is a function of the time. So what we can do is we've got our new formula equals, it says Q of t is equal to 10 times e to the 0.0139 t, right? That's our formula. So we have a quantity and we're trying to solve for a time period. So we're going to plug 20 in for that Q of t amount. And we're going to go through all the same steps here to solve for t that we did just before to solve for r. Meaning we're going to start by dividing both sides by 10. 20 divided by 10 is going to be 2. And now we're going to switch it from exponential into logarithmic. So it's 2 equals e to the 0.0139 t. So we're going to say the natural log of 2, which we could write that as log base e. But again, the natural log of 2 is equal to that exponent, 0.0139 t. So from here, again, just like I did above when I said when we had that step where it was the natural log of 4 equaled 100r, and I said don't evaluate the natural log of 4 yet, wait. And so again, in this one, we have the natural log of 2 is equal to something times our variable. So we need to, again, isolate that variable by dividing both sides by 0.0139. And once we do that, we can go into Desmos and we'll do the natural log of 2 divided by 0.0139. And we get that t is equal to 49.8667, blah, blah, blah. So we'll say t is approximately equal to 50 days. So questions about the process that I've done so far. This is a totally new thing that we're dealing with. So I understand if it feels like I'm speaking French here, or Chinese, or any other language that you don't know. So part C, I'm just going to zoom out just a little bit. It says part C says, when will the mice population exceed 100? So if we're looking at the population exceeding 100, so we're looking at when is Q of t, excuse me, greater than 100? Well, we can't have a partial mouse, right? We can't have like, well, when is it 100.5? So what we're going to do is, if we're looking for it to exceed 100, we're going to say let Q of t equal 101. Okay. So if we let Q of t equal 101, we've got, again, our formula, Q of t equals 10 times e to the 0.0139 t. So if we're letting Q of t, our quantity after a certain period of time, be 101, what we're going to do then is plug that 101 in for Q of t. And solve. So I want you to think about, again, I'm going to zoom out so you can see what I did in both part A and part B. The steps are exactly the same. And I want you to solve for t and let me know what you get in the direct message. So think about first steps, right? Our first step is to divide both sides by 10. So 101 divided by 10 is going to give us 10.1. We're going to switch this into logarithmic form, which is ln of 10.1, because it's ln base e, is equal to 0.0139 t. From here, we'll divide both sides by 0.0139. Those will cancel. And then we'll go to our calculator and do ln of 10.1 divided by 0.0139. And this gives us t is equal to 166 point, and then it gives 3694, blah, blah, blah. So I'm just going to round this to 166.4 days. Okay. So I've been teaching you that you're just going to take these exponentials equations and you'll rewrite them in logarithmic. I do want to show you a technique that some teachers use so that if you're in the FNC, it doesn't completely throw you off, or if you're looking at the how to solve this in Pearson, you're like, what are they even talking about? Aaron didn't show us this. So one of the things that you will see people do, let me get this new piece of paper, is with our formula, we had 101 equals 10 times e to the 0.0139 t. So a method that they'll use here to solve this is called taking the log of both sides. And so what that would look like, this is an alternative method to solve, okay? Taking the log of both sides looks like ln of 101. Oh, sorry. Before they take the log, you still have to isolate. That step is still the same. So we'll divide both sides by 10. So 101 divided by 10 is going to be 10.1 equals e to the 0.0139 t. Okay, so we're going to take the natural log of both sides. So we're going to say ln of 10.1 is equal to ln of e to the 0.0139 t. Now, when we're in this step here, we have something called the power rule. And this was listed in your notes for, what was it, 5E, I believe. Do we have a power rule there? We did. But I didn't really go over it because I didn't want us to get caught up in it. But if you're looking at 5E in the power rule, it says that the log base b of a to the k is equal to k times log base b of a. And what that's saying is it's taking this exponent and it brings it down in front. And that's kind of how they're solving these. So in this situation, I would be taking this and I would be bringing it down in front. So what that gives us is this. And then they have the identity, the natural log identity. So we have the identity that says the natural log of e is equal to 1, that identity. Okay, so what that means is that this piece right here equals 1, which allows us to write this as, and then we get to the point of where I was to begin with, right? And so all I'm trying to show you is that there's alternative ways to solve these. Sorry, my Apple Pencil is dying. I need to solve chart for a second. There's alternative ways to solve these. And I just wanted to show you, in case you're looking at the notes or talking with another instructor or something else. I will use this method, especially when we get to using normal logs instead of natural logs, because with natural logs, you've got the natural log of e, which turns to 1 and it drops out. When we get into some of the farther problems into this section, and we have to use logs and not natural logs, it does have it so where we can't just like throw a piece of it away because it equals 1. And so I did want to show you this process so that when I get to those, it doesn't seem weird. Okay. All right. So in number 1, they gave us the they gave us some information. They said, write the equation. Now in number 2, they're giving us this equation. So it says the number of milligrams of a drug still remaining in a patient after T hours is modeled with the function R of T equals 10 times E to the negative 0.2 T. And part A says, find the amount of drug remaining in the patient after 3 hours. So what I want you to do is I want you to evaluate that equation, right? We've got R of T, equals 10 times E. And if we're looking at 3 hours, that means we're going to let T equal 3. So E to the negative 0.2 times 3. So I want you to go ahead and tell me how much drug is remaining in the patient. You can round to the nearest hundredths, so 2 decimal places, okay? So go ahead and evaluate that, just the stuff that's on the right-hand side, and send me your answer in a direct message. Okay, so if we evaluate this, we plug this in, we're going to have, I'm going to go 10 times E, and then we're going to do that exponent. Now in the exponent, we need to have the parentheses so we can put the whole negative 0.2 times 3 part, all of that up there, right? And so this tells us that we're going to have 5.48811, blah, blah, blah. So we're going to say that we have approximately 5.49 milligrams. And so they do use these types of equations in order to calculate the amount of drug as it's being metabolized in a human body. And not this very specific equation, they use similar equations in order to make sure that you have enough time for the drug to reach a level in your system that where you, if you take your next dose, you're not going to overdose yourself, right? So again, really applicable to what we have in our world. So part B says, when will the amount of drug be 0.8 milligrams? And so R of T, what that means is amount remaining after T hours. That's what that R of T portion means. And so also, if we think about how this compares to our formula we had before, right? We have Q of T equals Q sub 0 times E to the RT. So remember, Q sub 0 is the original amount or the initial quantity. So in our formula, our initial quantity was 10, right? That 10 is in the same position as the Q sub 0. So in part B, it says, when will the amount be 0.8 milligrams? So what they're saying is, let's let R of T equal 0.8, right? We're trying to evaluate when that time, how much time needs to pass in order for the 10 milligrams to turn into 0.8 milligrams. So if we plug that in, we're going to say 0.8 is equal to 10 times E to the negative 0.2 T. And so now we're going to go through all the same steps that we were just going through in part 1 or in number 1, where we've got to isolate E to that exponent, and then we need to use those natural logs to solve for T. So again, what are those steps? We're going to divide both sides by 10. So 0.8 divided by 10 is going to be 0.08. And now, again, you have your choice. You can switch this into logarithmic form, right? Or you can choose to take the log of both sides. Either of those processes are going to work. If we choose the newer method, which is taking the log of both sides, we'll do the natural log of 0.08. Equals the natural log of E to the negative 0.2 T. We can use that power rule that I was talking about to bring the exponent down in front. And so we'll have the natural log of 0.08 equals negative 0.2 T times the natural log of E. Because we know that natural log of E is equal to 1, we can drop that portion off, which gives us the natural log of 0.08 equal to negative 0.2 T. And then we can use our final step, which is to solve for T by dividing both sides by negative 0.2. So going into Desmos, we'll do the natural log of 0.08. And then we'll divide that by negative 0.2. And that gives us T is approximately equal to 12.6 hours, right? And yes, I know I'm rounding down. So if you would feel more comfortable saying, well, Erin, really, it's more like 12.63 hours, right? You need to make sure that you have enough time for it to get to that 0.8. Again, I understand. We're in the theoretical world right now, right? So the last part of this question is part C. It says, what is the half-life of the drug? And so in number 1, it said, when would the population double, right? That was times 2. So now the idea of a half-life is, when is there half as much? Okay, so when will there be, oh my goodness. And it's like, when will there be half the original amount? So that's where the initial part, when I was talking about looking at that formula and identifying what those pieces are, that 10 that's in front of E tells us what our initial quantity was. Our initial quantity was 10 milligrams, right? So we want to know, when will there be half of that? So the initial amount was 10. Oops, let me write that better. 10 milligrams. So we're saying, what is T when R of T is equal to 5, right? Because we're looking for half that amount. So half of 10 is 5. So we'll set up that equation that says 5 equals 10 times E to the negative 0.2 T. And so I want you to go ahead and solve that for T and send me your answer in a direct message, please. Okay, so just as like we've been doing, our first step here is going to be divide both sides by 10. Right, so dividing both sides by 10 gets us 0.5 is equal to e to the negative 0.2 t. We will take, make sure that looks more like a t. We'll take the natural log of both sides because we're dealing with e. Okay. The exponent portion comes down, right? The power rule makes it come down here. So we'll have the natural log of 0.5 is equal to negative 0.2 t times the natural log of e, which again, that part drops off. So we have the natural log of 0.5 is equal to negative 0.2 t, dividing both sides by negative 0.2. And we get t is equal to what? Oh, let's go here. ln of 0.5 divided by negative 0.2. We get 3.5-ish hours. Okay. So what have we looked at so far? What are the applications? We've looked at population growth with mice, right? We've looked at quantity decay, right, with drugs for metabolize, right, your body's metabolizing. With that concept of decay and half-life, something you hear a lot about is carbon dating. And we look at what the half-life is of carbon. So there is a formula, or there are formulas, I should say, that measure the amount of carbon that's left in a organic object that allows us to know how old it is, right? So that's another application that we would be using logs for. in the world, I mean. And then as we talked before, compound interest, right? So the idea of continuously compounding interest, we have that formula, A equals P times E to the RT. Again, A is your balance, P is your principal or your initial investment, E is that number that we deal with, R is your interest rate expressed as a decimal, and T is your time in years. So number one says find the interest rate for a $10,000 investment, which grew to $14,000 after 3 years. Write the exponential growth model for this investment. So what they don't tell us is that they want us to write the continuous exponential growth. In your homework, it'll say continuous or not. So I just want to draw attention to that. I know I didn't write, I know I didn't say continuous here, and I apologize, but that is an important piece that you need to make sure that you have. So we want to say write the continuous exponential growth function. Okay, so we've got A equals P times E to the RT. So $10,000 is our initial investment, so that's going to be P. It's growing to 14,000, so that's our A value. It's our account balance after a specific period of time. And then after 3 years means that T is equal to 3. Again, we're trying to find that interest rate. That's why we don't have an R value here. So we're going to plug in what we have and go from there. So plugging in 14,000 for our account balance, 10,000 for our principal, times E, and then we have R times 3. Make that 3 a little clearer. There we go. So again, I know it kind of seems ridiculous, but our steps are the exact same, right? We are perpetually solving for that variable in that exponent, and therefore we're going to isolate E. We're going to then take the natural log. We'll do some division, right? So our first step, divide both sides by 10,000. Okay, 14,000 divided by 10,000, that is going to be 1.4. And you can write it as R3 or 3R, right? I prefer to write the number in front of my variable. Again, because of the rules of multiplication, they're equivalent. Now that we're down to this formula or this equation, we are again going to take the natural log of both sides. Like I said, we're just going to keep doing those same steps every single time. So the natural log of 1.4 is equal to the natural log of E to the 3R. We'll use the power rule to bring that exponent down. So I have the natural log of 1.4 is equal to 3R times the natural log of E. Because the natural log of E is 1, we can drop that. And we have the natural log of 1.4 is equal to 3R. And then our final step is to divide by 3. So over in our calculator, we'll do the natural log of 1.4 divided by 3 gives us 0.112. You can keep going. I'm going to keep going. Your homework will tell you how many decimal places to take it out to. But this gives us 0.1122. So they want us to write the formal final equation. And so what that's going to look like is A is equal to 10,000 times E to the 0.1122 T. And that would be the very final model that we would use for this investment, so that if any time we're trying to find how long it takes to get to a certain value, or if we invest for a certain period of time, what would our value be? This would be the model that we would use now that we know our interest rate. So we're going to go to number 2. I'm going to copy this formula so that we have it for part 2. So if we go to the next page, it says find the doubling time using the interest rate in part 1. So let me paste that over here. So we've got it. So again, doubling time, that means twice as much. So again, how long until the balance is twice the initial investment? So again, we need to remember, what was our initial investment? Our initial investment was 10,000. So if we're looking at twice as much as that, that's looking for 20,000. So we'll plug that 20,000 in to our formula. And we will solve for t. So I'm going to go ahead and let you solve for t here, letting the machine catch up. There you go. So go ahead and solve for t there and send me your answer in a direct message, please. So again, those steps, we're going to divide both sides by 10,000. So 20,000 divided by 10,000, it's going to be 2. Take the natural log of both sides. Bring the exponent down. Drop the ln of e part because again, it equals 1, right? So we'll have the natural log of 2 is equal to 0.1122t. Divide both sides by 0.1122. And going over to our calculator, we'll do natural log of 2 divided by 0.1122 gives us 6.177 blah blah blah, and we'll do approximately 6.18 years, right? And because it's continuously compounding, we can have a portion of the year, right? Because at any given time, you will be having that amount, right? So where in the mouse problem, we're looking at what point are we going to have a certain quantity of mice? We have to round to the nearest whole mouse, where with time, we can have a portion of time, especially when we're looking at this continuous situation. Now, our next example is getting away from our use of E in this continuous model. And so this is where we're going to have to switch from using natural logs to using logarithms, right? The standard log base 10. So the example says the total number A of t, amount after a certain time, of asteroids t years after 1990 can be estimated by A of t equals 77 times 1.283 to the t. It says determine the year in which the number of asteroids first reached 4,000, round to the nearest tenth of a year. So what we're doing is we're looking at how long does it take for A of t to equal 4,000, right? So we're going to plug 4,000 in for A of t. And we're going to start solving this the same way, right? We've got some value times some value to an exponent, right? So we're going to start by dividing both sides by 77. So when you're working on these problems, if you go over to your calculator and you're like, okay, well, I'm just going to take 4,000 and I'm going to divide it by 77, and you get this decimal, you can see here, 51.94, blah, blah, blah. And you're like, oh, well, shoot, that doesn't reduce, right? So that tells you leave this as a fraction. You're going to need it that way later. So what we're going to do is we're just going to say 4,000 over 77. And I know this is uncomfortable, but we're trying to have the most accurate answer possible. And that tells us we don't want to round in between, okay? So now that we're in this spot, we're going to take the log of both sides, okay? So I've got the log of 4,000 divided by 77 equals the log of 1.283 to the t. Now, this is where that power rule is going to come into play. We're going to bring that exponent down in front. And what that gives us is the log of 4,000 divided by 77 equals t times the log of 1.283. Now, in the last example, we had the log of e, the natural log of e on the end, and we're like, forget it. We don't need to deal with it because that's equal to 1. In this case, the log of 1.283 is not equal to 1, and we can't just drop it off. So what we need to do is we now need to divide both sides by that log to isolate t. So dividing both sides by log of 1.283. This allows those to cancel. And t is equal to this crazy thing, right? It says the log of 4,000 over 77 divided by the log of 1.283. And you're like, I have no idea what that is. That's okay. That's what we have decimals for, right? They are going to do the calculation for us. Now, looking at this, don't try to cancel those word logs out or anything like that. Remember that whole thing in the numerator is a number, and the whole thing in the denominator is a number as well. So when we go to Desmos, we want it to evaluate this whole thing for us. So I'm going to press the division key first. What this does is gives me that fraction and allows me to enter the whole numerator. So I'm going to say log and then parenthesis, and I'm going to do 4,000 divided by 77. You'll notice I didn't go into the functions to try to find a log with a specific base, because when we just write the word log, the calculator assumes and knows that we mean base 10. And since we don't have a specific base written as like the little subscript below the G, we know that we're just dealing with normal logs here. Now, once we have that numerator, we'll click into the denominator or use your down arrow key. That will get you into the denominator. And we're going to type log and then in parentheses 1.283. And so again, what this does is Desmos calculates all of these pieces, right? It first does the 4,000 divided by 77, takes the log of that, takes log of the denominator, then divides those two. All sorts of calculations that we don't need to do, we'll let them do, and it gives us the most accurate answer. So what we're given is that t is equal to 15 point, and it says round to the nearest tenth of a year. So I'm going to do 15.9 years. So it's going to take 15.9 years, but there's a little piece here that we need to make sure that we go back to. And it says, determine the year in which this happens. Well, we know it's going to take 15.9 years for it to happen, but the specific year it will happen in all depends on where are we starting this model from. And the starting is at 1990. So what that tells us is we need to take 1990 and add 15.9 years onto it, which I'm not even going to try to do it in my head. I could, but I don't want to. And that means it's going to happen in the year 2005.9 or approximately 2006. So again, you have a problem that's similar to this. You have to look at what is it asking. It's measuring from a specific time period, right? From the year 1990. And then you're figuring out how many years it takes. And then you have to answer it as if we're looking at a real year in history and not saying it's year 15.9. No, it takes 15.9 years to get there. But then the year it actually takes place in is 2006. Okay. Part B doesn't care about the year in terms of our time. It just says how many years will it take. So part B says, what is the doubling time for the number of known asteroids? So our formula is A of t equals 77 times 1.283. Goodness. 83 to the t. And you might be saying to yourself, well, Erin, if we're going to find the doubling time, we need to know what the initial quantity was, right? And they didn't talk to us about the initial quantity. And that's why it's really helpful to be able to look at the formula and compare it to what formulas we already know. And one of those is our exponential growth function. In the exponential growth function, remember it said Q of t equals Q sub 0 times 1 plus R to the t. And this function, where did we see this? This would have been back in five. Yeah, 5 A, right? We looked at this formula. So if we make this measure, like we compare this, we've got 77 times 1.283 to the t. So looking at how those pieces compare, we can see that our initial quantity, Q sub 0, was 77 because it's in that same position, right? We can see our interest rate in this case, or our growth rate, excuse me, because we're not talking about money, is 0.283, right? Because if we do 1 plus R is equal to 1.283, R is equal to that 0.283. So again, going back to what do we know about these types of models is going to be helpful. So if we're looking for that doubling time, we're saying, when will we have 2 times that initial quantity? So 2 times 77 is going to be 154. So that's what we're going to let our A of t equal. So we'll do 154 equals 77 times 1.283 to the t. Excuse me. All right. So we're now dealing with those logs, right? It's a little bit different. I want you to try this one. Okay, think about the steps I took in part A, and send me your answer in a direct message round to the nearest tenth of a year. Okay. So again, you're solving for T in that formula right there. Okay, so what are our steps here? Our first step is we're going to divide both sides by 77, right? Because we're always trying to get out what's being raised to that exponent. 154 divided by 77, we know what that's going to be because we multiplied 77 by 2 to get the 154. So we now have 2 equals 1.283 to the t. We're going to take the log of both sides. Again, we're dealing with just normal logs because of the fact that we no longer have that base e. So we're not bringing natural logs into the mix. Once we take the log of both sides, we will bring that exponent down in front. And then we will divide both sides by log of 1.283. Those will cancel out. Going over to our calculator, we're going to say log of 2 divided by log of 1.283. And we get t is equal to 2.7814, blah, blah, blah. So approximately 2.8 years. So it'll take 2.8 years for the number of known asteroids to double. Okay, so our last example that we're going to look at, it has to do with loudness. So loudness has kind of a crazy formula. So L is equal to 10 times the log of I over I sub 0. And so this is, there's a set of parentheses here. So this is I as in the letter I, right? And I is measured the intensity. I sub 0 is 10 to the negative 12 watts per meter squared. 10 to the negative 12 watts per meter squared is considered the softest audible sound. It's the softest sound that can be measured, we can hear. So if we rewrite this formula, instead of the I sub 0, it's going to be L equals 10 times the log of I over 10 to the negative 12, right? So what do we do with this? Why do we care about this? Well, in number one, it says sound level of 90 decibels and above are considered unsafe. What is the intensity of these sounds? So this 90 decibels, that is the loudness. That's how loud it is. So we're going to plug that 90 in for L and solve. So we're going to say 90 is equal to 10 times the log of I over 10 to the negative 12th. So when we've been solving these problems previously, we haven't had the log already. We've had it in exponential form, right? And we've been using logs. So what we're going to do now is we're going to undo this. In order to get to that log, we need to first divide both sides by 10. So dividing both sides by 10, we're going to say 90 divided by 10, which is going to be 9. So we have 9 equals the log of I over 10 to the negative 12th. Now remember, if the word log is just there, the assumed base is 10. So we're going to write a little 10 here in order to remind ourselves of that. Now, we want to switch this out of logarithmic format, right? And so remember, we're going to take the base of the log, 10, raise it to the power of the value that's being isolated on the other side of the equal sign, and that's equal to the amount that is in the log, remember correctly? So if we think back to our work that we had done previously, I always want to make sure that I get all of our formulas the same. So if we have, just want to go back to what we already know. If I had log base A of x equals m, remember to switch this out of logarithmic format. I'm going to say a to the m equals x, right? That's how we are switching back and forth between those. So going down to my formula, 9 equals log base 10 of I over 10 to the negative 12th. I'm going to take this base of 10, raise it to the 9th. We'll say 10 to the 9th equals the stuff that's inside. So that's equal to I, oops, let me not have this I be crazy, I over 10 to the negative 12. So the last step is to solve for I, right? And if we're dividing by 10 to the negative 12, in order to solve for I, we're going to multiply both sides by 10 to the negative 12. So multiplying by 10 to the negative 12, these will cancel. And so I is equal to 10 to the 9th times 10 to the negative 12th. And remember how we talked about powers of 10 and simplifying those way back in the beginning of the semester. Again, it's all coming around. There's a reason when we do any of the things, right? They all connect to each other. So remember, in order to simplify this, I'm going to rewrite that base, add those exponents. 9 plus negative 12 is going to make negative 3. And our final answer is the intensity of that sound is 10 to the negative 3rd, or 0.001 watts per meter squared. And that is the sound level. So 90 decibels is actually like, it's pretty loud, but you don't realize how loud it is. Where I live in Tennessee, there's the University of Tennessee, and there's Neyland Stadium, which is their stadium, and it's actually one of the largest stadiums and the loudest stadiums. And so they measure the loudness all the time, and like you can be at a football game there and like the sound level is like 110 decibels. Like it's crazy loud. And so a lot of people wear earplugs, and I didn't the first time I went, and my ears were ringing. It was terrible. All right. We have
how you got the 10 to the 9 again.
Oh, I took the base right here and I raised it to the exponent of 9, right? You're taking that base, raising it to the value that's away from the equal sign, right? And then it's equal to the value that's inside the log.
Okay, and you can only do that with logs?
Yes.
Or is that how? Okay.
Yeah. So when you have it in logarithmic form and you're trying to put it in exponential form, that's how you would go through that process.
Okay.
Yeah. Yeah, so to go from, like if I look at the top here, to go from this format to this format, that's the process I use, right?
Oh, okay.
Yeah. All right, I'm gonna leave number 2 until we come back together because we did a lot of stuff. And I don't want to, we only have like 3 minutes left, and I don't want to rush us to try to get through part number 2 there. So we'll just cover that on Tuesday when we come back together, okay? So that little piece that I'll finish on Tuesday, that is the last of new material. Next week, you have test 5 due. Test 5 is not due till Thursday to give you some time to finish it up, because there's no way you can take a test between now and Tuesday of next week. So you have until Thursday of next week to take test 5. On Tuesday, I'm going to go over this little amount, and then we are going to spend the rest of the time talking about the final exam and starting to review for the final. And I'll give more information about the final exam on Tuesday of next week, okay? So, any questions before I let you go today?
I'm good. It was kind of confusing at the beginning, but pretty good now.
Okay. What about everybody else? We don't want to let Luke speak for everyone, right? We all have questions. Well, don't forget to get your buying versus renting project in, right? That's due tonight. Yes, am I correct? Or was it due last
Yes, you're correct.
night? It's due tonight. So
Yeah.
we want to do it.
Then 5F due tomorrow, or is that 5D?
5E is due tomorrow.
5E.
5F's not due till next week.
Okay, sweet.
Yeah. Okay. Well, that's everything. I hope you guys have a good weekend. Always send me emails, right? And I will see you on Tuesday.
Great. Thank you. Have a good weekend.
All right. Bye, everyone.